Hello and welcome back. In this section, section 3.5, we'll be looking at rational functions. We've already seen rational equations before, and so this should be somewhat familiar. Rational functions are quotients of polynomials, meaning it's just a polynomial divided by a polynomial. A very natural generalization of a polynomial function. And the domain of any function will simply be what numbers we can plug in. So if we have a rational function, well, we can plug any number we want into a polynomial, but when we're dividing by a polynomial, we have the only restriction being we can't divide by 0. So the bottom of the fraction just can't be 0. So let's take a look at some rational functions and find their domains. For this first function, we've got x squared minus 25 over x minus 5. This is a polynomial divided by another polynomial, so this is a rational function. And furthermore, we want to find the domain. So we just want to ask, when is the denominator 0? We need to take that out. We can't divide by 0. So let's solve when is x minus 5 equal to 0? Well, if I add 5 to both sides, we get that x will be equal to 5. So this cannot be part of the domain. So this is not in the domain. So we need every number except 5. So if I were to write the domain down, it's all the numbers from negative infinity up to 5, but not including 5. And furthermore, every number from 5 and up, so every number from 5 to infinity. And I need to put these two sets together, so I take their union. And there we go. There's the domain of this function. Here's a little bit more work in this one. So this function, we've got x divided by x squared minus 25. Again, a polynomial divided by a polynomial. This is rational. So we need to solve when is the bottom of this fraction equal to 0. These numbers can't be in the domain. So x squared minus 25, that's the same thing as x squared minus 5 squared, so this factors very easily. This is x minus 5 and x plus 5, just a handy little trick. So when this is equal to 0, there are two numbers that will solve this. Either when x minus 5 is equal to 0, so we have x is equal to 5. If I plug a 5 in here, I get 0 times something is 0. Over here, I'll get x is equal to negative 5. If I solve this is equal to 0, I'll get that x is equal to negative 5. So these two numbers can't be in the domain. I can't plug in a 5, and I can't plug a negative 5 into this function. So again, if I were to write down the domain of this function, maybe drawing a picture will be a little bit helpful here. If I have my number line, maybe we've got 0 in the middle, we've got negative 5 down there and 5 up there. I have to skip the number 5 and the number negative 5. So if I do this in red, I have to skip the number negative 5, I have to skip the number 5, but it should be everything else in between and off to the sides. So if I do this region note down here, this is all the numbers from negative infinity up to negative 5. The region in between is all the numbers from negative 5. Let me give myself some more space. All the numbers from negative 5 up to 5. And if I look at this region over here, this is all the numbers from 5 on up. I can't include 5 and negative 5, so I have to use parentheses. And again, I glue them together using a union. The last function over here, we have x squared plus 25. I can't let the denominator be equal to 0. And here, let me do this in the following way. If I subtract 25 from both sides, get negative 25. So x is either going to be the square root of negative 25, or x will be the negative square root of negative 25. But the square root of negative 25, that's an imaginary number. It's going to be 5 times I, or x will be negative 5 times I, because again, I'm taking the square root of a negative number. The domain of a function is only going to be real numbers. So if the only things that I can't plug into the domain are imaginary numbers, I can plug in any real number I want. The domain of this function is going to be all real numbers from negative infinity up to infinity. These are not real numbers. I don't have to take them out. And my domain is everything. No matter what I plug into the bottom, it will never be equal to 0. So next up, I want to look at a very specific function. This is the function 1 over x. And I want to see what happens, what is the end behavior of this function. So again, with end behavior, this means I want to know what happens as x gets really, really big. So as we go farther and farther to the right, or if we go farther and farther to the left, what ends up happening? Well, if I plug a 1 in here, 1 divided by 1 is 1. 1 divided by 10 is 1/10. 1 divided by 100 is going to be 1/100th, or divided by 1,000 will be 1/1000th. So as x gets bigger and bigger and bigger, we're getting closer and closer to 0. And these numbers are pretty small in value. So we're getting closer and closer to 0. If I plug in a negative number, well, 1 divided by negative 1 is negative 1. 1 divided by negative 10 is negative 1/10. And we can begin to see the pattern here. So if we start at negative 1 and we're going to the left, we can see that we're also just getting closer and closer to 0. And so far, so good. So what happens in between? What happens when we plug in really small numbers, or I should say numbers that are close to 0? So let me fill this in for a second. So we know that as we get really big, we get close to 0, and as we get really negative, we get close to 0. So what happens as the x gets closer to 0? Well, 1 divided by 1 is 1. 1/10, 1 divided by 1/10 is 10. 1 divided by 1/100th is 100. 1 divided by 1/1000th is 1000. So as I get closer to 0, our numbers, the function value is going up. One way to think of this, if you divide 1 by a small number, you get a big number. Likewise, this negative sign just sort of pops out, and everything works pretty much exactly the same. For instance, 1 divided by negative 1/1000th is negative 1000. So as we get closer to 0 from the other side, as x approaches 0, f of x is going to negative infinity. It's getting really, really negative. So we have some notation for this. So we can say, for instance, as x approaches infinity. So what this means is that x is getting really big. X is getting closer and closer and closer to infinity. This doesn't necessarily make sense. Infinity isn't a fixed number. We can't really get close to it. What this means is x is increasing without stopping, without bound. It's getting bigger than anything. As x goes to infinity, as x goes further and further to the right along our graph, what happens to the height of the function? The height of the function is f of x, and this is approaching 0. So this arrow means approaches, or gets close to. If we go in the other direction, as x goes to negative infinity, what's happening to the height of our function? Well, again, it's getting close to 0. Now it's getting close to 0 from the bottom, but it's still getting close to 0. So f of x is going to 0. Now we have to be a little bit careful. If I want to know what happens as x gets close to 0, so as I start plugging in x values that are closer and closer to 0, where the function goes depends on if we're getting closer to 0 on the right side or if we're getting closer to 0 on the left side. On the right side, we're going up. On the left side, we're going down. So we have some notation for this. Let me scroll up just a little bit. So we can say as x goes to 0 from the right, and I'll put a little plus sign to say on the positive side. Or as x goes to 0 on the left side, we'll add a little negative sign. Note that this doesn't mean positive 0, it means 0 on the right side, and this means 0 on the left side. So if we approach 0 on the right side, we can see that we're going up, we're getting big, and we're not stopping, we're getting bigger and bigger and bigger. So f of x is approaching infinity. But as we approach 0 on the left-hand side, f of x is approaching negative infinity, as in it's going down without stopping. So again, with this notation, if you are approaching some number a, the plus sign means that we're approaching from the right-hand side. The negative sign means that we're approaching a from the left-hand side. As so arrow infinity means that we're approaching infinity, meaning we're going forever to the right, and x approaching negative infinity means that we're approaching negative infinity, as in we're going forever to the left-hand side. So here's another function. F of x is 1 over x squared, and we can see that as x approaches infinity, so we look at this and we go, okay, so as we get bigger and bigger and bigger, as x goes out here, what's happening to the function? Well, it's getting closer and closer to 0. For instance, here x is as x approaches negative infinity, so as we go off the left-hand side, what's happening to the height? It's also getting really small. It's getting closer and closer to 0. Here, if we approach 0, so here's 0, as we approach 0 from the right-hand side, hence the plus, we're going up, and we're not stopping, so we're going off to infinity. Here, as we approach 0 from the left-hand side, hence the negative sign, we are also going up. So f of x is approaching infinity no matter what, if we approach from the right-hand side or from the left-hand side. This phenomenon right here is called a vertical asymptote. And the idea is that our function, as we get close to 0, our function shoots up, or it could be shooting down. But as long as it goes to infinity, this is what's called a vertical asymptote. So again, if you have a line, x is equal to a, so this is a vertical line, this is called an asymptote. If the function shoots off to negative infinity as we get closer to the line, or it shoots off to plus infinity as we get closer to the line. And again, we could be going to negative infinity from the left, we could be going to negative infinity from the right, we could be going to positive infinity from the left, or we could be going to positive infinity from the right. In any one of these scenarios, we call this a vertical asymptote. As in, as we get close to a, either from the left-hand side or the right-hand side, we shoot off either toward negative infinity or positive infinity. So the question is, how do we find these? How do we know if there's going to be a vertical asymptote in our function? And the answer is, essentially, the line x is equal to a is going to be a vertical asymptote if there's two things. One is that we're dividing by 0 at that point. So as you get close to a, if you were to actually plug a into your function and we see that we're dividing by 0, this is a strong indication that it's a vertical asymptote, but it's not quite enough. The other thing that you need to check is that P and Q can't have any common factors. And this is what I'll do in the next video. We'll go through vertical asymptotes before we also go through horizontal asymptotes.